Welcome to the second part of the problem-solving session for Chapter 30. Let's begin where we left off in Part 1. Here we start with question 5, and we're told that we have a wire, which we're calling wire 1, and if you notice here, our wire 1 is a straight and long wire. Carries a current I1 in the positive j-hat direction. Meanwhile, we have a loop, which is this rectangular loop that you see right here, placed at a distance little a from the long wire, and this loop also carries current, and as you can see, the current on this loop is in the positive j-hat direction on the leftmost side, on the positive I-hat direction at the top, in the negative j-hat direction on the rightmost side, and then in the negative I-hat direction at the bottom. And we're asked to determine the magnetic force that wire 1, the very long wire, exerts on simply the top side of the loop. So in other words, first, let's just go ahead and consider along here, the top, what the magnetic force is. And then, in fact, although the problem doesn't ask us to, we can go ahead and determine what it might be for the two sides that are parallel with wire 1, and of course also the bottom side. Well, the first thing that we note is that because wire 1 carries the current, it produces a magnetic field. On the right side of the wire 1, you can see that the magnetic field points in. On the left side, it comes out. Now, we don't care about what is happening on the left side of wire 1 because the loop, the thing for which we are calculating the magnetic force, is only on the right side. So we begin with the magnetic field at this point here, which we call point A, and let me see why my pencil is not writing here, which is at a distance A from wire 1, and we end at the point B, at not necessarily the point B, but at a distance A plus B from the wire that produces the magnetic field. So what you can see is that the magnetic field varies from here, this being our initial, to here, this being our final. In other words, the magnetic field is getting weaker as we consider the values of B moving away from the initial position. And what we find here is that the magnetic field produced by wire 1 is given by mu naught I1 divided by 2 pi, and x here, the x just means the point which will vary from initial to final. And you can see that the direction of B1 is in the negative k-hat direction. So to get the magnetic force, we have to consider that as the magnetic field weakens from the initial to the final position, so would the force, because in Chapter 29, we saw that the force FB, was given by I here being the I of the loop, which we call I2, times L, the length, cross B, the magnetic field, which in this case is the magnetic field that's produced by wire 1. Now the problem that we face is, though, that the magnetic field changes with every ds, and so that the value of B is not constant over the whole length of the wire. So the only thing that we can really do is to initially set it up for a small segment, what we're going to call ds, or rather dx. Okay, the little ds that you see here, which is going to be in the x-axis, we're going to call that dx, which is in the I hat direction, and we're going to cross it with b, magnitude of b1, which I'll go ahead and write down is in the negative k hat direction. And we're going to have to, of course, integrate and consider all the values of b from initial to final. Well, let's see. Let's go ahead and set up our integral fb on wire 2 due to wire 1. Well, the I2 is going to be constant, so we pull that out. And the magnitude of b1 is a constant, so we'll pull that. Well, actually, it's not a constant, is it? Nope, we can't do that. Nope. Let's see. We're going to integrate. Let me go ahead and just erase this because that's not quite correct what I said. So we can pull out the I2 because that is constant throughout, but our integral is going to be dx I hat cross b1 minus k hat. And if we look at the cross product of I hat cross negative k hat, that gives us a positive j hat direction. And so in this case here, the magnetic force will be in the positive j hat direction, and we can go ahead and write down now the magnitude of dx times b1. Well, b1 is mu naught I1 over 2 pi x. The direction, of course, is positive j hat, so we'll just place it right here. And let's go ahead and pull out all the constants. We're going to have the ends of the integral 2 to work out. So let's go ahead and pull out mu naught I1 times I2. So I'm just rearranging the order of the terms here. Mu naught I1 times I2 divided by 2 pi, and we're in the positive j hat direction, so I'll go ahead and pull the unit vector out, times the integral of dx over x. So dx over x, because I pulled all the constants out, including the direction. And x begins at a, so we're going to measure beginning at the position a and ending at a plus b. So this is the integral that we need to worry about. This integral right here is ln of x from a plus b, so in other words, from a to a plus b. And so what we're going to be left with here on the top part is mu naught I1 times I2 divided by 2 pi ln a plus b over a, and this is in the j hat direction. So this is the magnetic field for the top part of the loop. Now, let's go ahead and see if we can work out for the sides. Let's look at the side right here, which is closest to the wire 1 at a distance a. Well, in this case here, notice that the value of the magnetic field is the same at every single point of this wire. And so B is not going to vary. In fact, at this location here, B1 is just simply equal to minus mu naught I1 over 2 pi A, and of course that's in the k hat. Here, B1 on the rightmost side is equal to minus mu naught I1 over 2 pi A plus B, and that's also in the minus k hat direction. At the bottom, similar to the top, is going to be B1 is going to be equal to minus mu naught I1 divided by 2 pi x in the minus k hat direction. So let's go ahead, because the bottom is going to be similar to the top, what's going to happen is, if you notice here, the magnetic force is in the positive j hat direction at the top. It's going to be in the minus j hat direction at the bottom. And if we were to add the top and the bottom, they would cancel each other out. But the magnetic force on the left side and on the right side of this loop is not going to cancel. And let's just see if we could work out what it would be. Well, FB on 2 at position A is going to be I2 times L, where L is going to be this length right here, this length right here, which was not really given to us, but we'll just call it L. And L, of course, is in the positive j hat direction. So direction-wise, it's positive j hat. And we're going to cross it with B1, which is in the negative k hat direction. And if you remember our little wheel, I hat cross j hat cross k hat, if we take j hat cross k hat, it's positive I hat, but because we're crossing it with negative k hat, the direction here is going to be in the minus I hat direction. And so let's go ahead and just put our direction there. But because B1 is constant, we write I2 times L, the length of the side, times, because we've already done the cross product of j hat cross negative k hat, B1, which is mu naught I1, I1 over 2 pi A. And if we rearrange these terms, clean this up a little bit, mu naught I1 times I2 times L over 2 pi A in the minus I hat direction. If we come back over here and notice that this time our current is in the minus j hat direction, we do the same thing, except this time, instead of positive j hat, we are in the minus j hat direction. B1 is still minus k hat. So this time we're going to cross minus j hat with minus k hat. Well, the minuses are going to cancel, and we'll end up with a force, so FB on 2, and this is the left side. On the right side, we're going to have positive I hat. That's right side, except the magnetic field is a little weaker, and in fact, instead of dividing by A, we divide by A plus B, so we end up with FB on 2 on the right side equals mu naught I1 times I2 times L divided by 2 pi A plus B. And if we wanted to, we could add these two terms and they would not cancel each other out because the denominators are not the same. Next question. Here we are given a wire that carries current through its interior. This wire has a thickness which is considerable, and we have to find the magnetic field inside the wire and outside the wire. And we're going to use Ampere's law to calculate the magnetic field inside and outside the wire. So let's begin by considering inside the wire is a little r, which is less than big R. This is in. outside the wire, R is greater than R. And let's go ahead and write down Ampere's law. It's the line integral, closed line integral of B dot ds, where ds is a loop, equals mu naught times I inside the closed loop. So let's begin with little r is less than big R. Well, if you notice that when we're here, we are only capturing part of the total current. In fact, the current that's inside this loop right here, this is our loop, our Amperian loop, divided by the area that loop encloses, pi little r squared, equals the total current, that is the total current that flows through the wire, which is given to us as I naught. Well, the naught here is just to tell us that it's the total current, divided by the total area. So what we're looking at is the current density. Well, the pi's are going to cancel, and so IN is going to equal the total current, I naught, times little r squared, divided by big R squared. Well, now we're prepared to go ahead and calculate, using Ampere's law, B dot ds. Well, B and ds are parallel, so we have just the product of B ds equals mu in, mu, let me go ahead and just erase that in part there, mu times I in, the current inside the Amperian loop. Well, we get B times the integral of ds, which is of course 2 pi little r, equals mu naught, sorry, that's the naught that I wanted there, times I total, or I naught as our book calls it, times r squared divided by capital R squared. And this is, of course, this little r cancels one of those. So we have, when we're solving for B, we divide both sides by 2 pi, and we get mu naught I times little r divided by 2 pi R squared. And this is, of course, the magnitude of B. And notice that everything here is constant, because R squared is just the radius of the wire, and that's constant. And so B actually increases outward from the center of the wire, directly proportional to R. It's a linear dependence of B onto R. Now let's go ahead and look at the magnetic field outside the wire. This time, when we consider Ampere's law, mu in equals I in, well, the total current inside the Amperian loop, here's our Amperian loop, the total current that's enclosed by that is I naught, I total. And so here we do not have to consider the current density because the total current is enclosed. And so here again, B and ds are parallel, and we can now, ds is of course 2 pi r, okay, the circumference of the Amperian loop. We solve for B, mu naught, I total, divided by, we're going to divide both sides by 2 pi r, and this gives us the value of B outside the wire. Next question. Here we're given a cube, a closed cube, of sides equal to 2.5 e to the minus 2 meters, placed in the direction given here, where there is a magnetic field which is constant and has the following I hat, J hat, and K hat components. The first question says, find the magnetic flux through the shaded face. That's this one right here. And then the next part says, find the total magnetic flux through all the faces. In other words, add up the contribution from each of the 6 faces and determine the total flux. Well, let's begin with A, and let's notice that to calculate the flux, the magnetic flux, we need the dot product, the scalar product of B and A. And what that means is that we need the area normal, which in this face, the area normal points in the I hat direction, so the vector A is L squared I hat. And so for the first part, we are going to take the dot product of B. Our B is, so here's the magnetic flux, 5 I hat plus 4J hat plus 3K hat Tesla, dotted with 2.5 e to the minus 2 meters squared in the I hat direction. And of course, I hat dot I hat equals 1, and J hat dot I hat is 0, K hat dot I hat is 0, so we only get the contribution of the I hat terms, and that gives us a value of 3.125 e to the minus 3 Tesla meters squared for the shaded face. Now, for part B, something to consider that for every I hat, when you add it with this area normal, we get L squared times minus I hat. Here we have our A, which is equal to L squared times positive J hat, but when you add it to the bottom, A equals L squared times negative J hat. For the front, you've got A equals L squared positive K hat, but then we have to add it to the back, which is in the negative K hat direction. The long and the short of it is that when you add up all the positive terms, see, this is a positive flux because it was I hat dot I hat. There would be a negative flux for the left side of the cube, which would add to 0, and then for the top would be a positive flux, but added to the bottom would be negative. And so the net flux in this closed surface is 0. But that's nothing more than Gauss's law, which told us that the flux through a closed surface is equal to 0. So Gauss's law, basically, if we consider Gauss's law here, B dot dA, we're considering Gauss's law for closed integrals of B dot dA, gives us 0, and that tells us that no monopoles exist, which is consistent with what we expected. When the surface is open, however, we do get a flux, and that's why this was non-zero. But as soon as we consider the flux through a closed surface, the net flux will be equal to 0. Well, this concludes the last part of the problem-solving session for Chapter 30. Until next time.